enormous pleasure to be back in Aberystwyth because I used to be their external examiner and enjoyed very much coming here. And when I became head of physics at FIRO, I was banned from being external examiner, so I missed my visits to Aber, so it's very nice to be back. The three lectures I'm going to do are loosely linked together into this quantum technology stuff. So what I'm going to do in the first lecture is to talk about non-classicality. In particular, what constitutes a completely non-classical behavior with light, and I'll start by doing that. The next lecture, I was going to start thinking about reservoir coupling, open systems, coherence. Can I just check with the audience, how many of you are familiar with master equations? Good, okay, that means I can cut some material out. Okay, so firstly, the first lecture I thought ought to be a little bit more gentle. So we'll have a few cheap jokes and things as we go along. As was mentioned in the intro, I am based part of the time at FIRO. I also run this Institute for the Royal Society at Chisley Hall up in Buckinghamshire. Okay, so let me start with a bit of history about photons. It goes back to Einstein and the idea of light quanta. And Einstein was absolutely revolutionary. And one of the problems that we have is this. That's the image of Einstein that everybody has in their heads. This lunatic elderly gent with white hair all over the place, wearing no socks. Okay? This is a complete travesty because what Einstein looked like when he did this stuff was that. Okay? He was a young man, and if you look at that photograph carefully, you can see this guy is a serious thinker that's going to cause trouble. Okay? So when you look at that one, that's the popular image. And it's so the general public will then think that distinguished scientists are elderly gents with white hair looking completely crazy. But in fact, he looked like that. Okay? So it's really important to actually, and he was really young when he did this sort of stuff. So what I want to talk about a little bit at the beginning is some wave-particle duality ideas. So this is something from Peter Maloney and his book Quantum Vacuum, which I hugely recommend. Peter was my first ever PhD student. It's really disconcerting when your first PhD student retires before you do. And he has now retired as T4 director at Los Alamos. But what Peter was always very fond of was pointing out that the Einstein fluctuation formula from about 1916, where Einstein tried to reconcile thermodynamic equilibrium and the black body formula, has something very peculiar within it. So let's look at the energy fluctuations in black body radiation. So we'll look at the variance in the energy. Okay, so the average of the energy squared minus the average energy squared. And if you go through the thermodynamics, it's just this. It's d by d temperature of the energy. But you know what the energy density is? It's the black body formula. Okay, so you just take the black body formula, shove it into there, and you work out the fluctuations. And if you do a little bit of work, and not very much work to be honest, plugging it into here, you find you've got two terms. So the energy fluctuations of frequency omega in black body radiation have two bits to them. There's that bit which depends on the density, and that bit that depends on the density squared. Okay? So if I translate that into numbers of quanta, by the way, that's the number of quanta, that's the number of quanta squared. If you go back through the analysis, you can locate that one as a particle term, as if there's a Poisson stream of particles. And that one is a wave term. Now, most people will tell you that if you do an analysis of an optical experiment, you either see the wave nature of light or the particle nature of light, depending on how you do your measurement. And the interesting thing about this formula is presumably the energy fluctuations of frequency omega are observable. So there's an experiment you could do. I don't think anybody's ever done it, which will show both particle and wave nature simultaneously. So the Planck formula has within it wave-particle duality in a most mysterious way, where at the same time you've got both bits in it. And I think that's kind of unusual, because most of the experiments you do, that you can think of doing even, the Gedanken experiments, will either show you wave nature or particle nature. But if you could measure the entropy fluctuation, as I said, I'm not sure anybody's ever done it. I can't locate anybody that's done it. You could actually show both. Right. So it's a little bit of elementary stuff on field quantization to get it to set the scene. So what we do is we decompose the field into a set of modes, and the modes are then treated as harmonic oscillators. So you have a big box, and you work out what the standing waves are in the big box, and then you've got this harmonic potential, and then you've got the ground state first excited and so on, and you climb the ladder of excitations with the creation operator, which acts on a number state with n excitations, takes you to n plus 1 each time. Okay, so let's start building some fields. Okay, now, first thing I want to do, I told you we want to start with something slightly light-hearted, is to prove that Shakespeare invented field quantization. Okay, that's Ian McKellen and Judy Dench. Okay, let's get some quotes up from Shakespeare. Okay, right. Is this a dagger? Well, remember the creation operator, a dagger, is the critical part of this. Okay, so you'd obviously thought about a dagger as the creation operator. There's the dagger. Okay, but look further down the quote. A false creation proceeding from the heat oppressed brain, the black body formula, in other words. So it's quite clear that in Macbeth, Shakespeare really is anticipating field quantization. And I would insist on that. Right, more seriously. Right, let's start thinking about field modes. Okay, there's a field operator. And one of the most bizarre things about field quantization, or any sort of electromagnetic field formula, is there's the positive frequency part of the field, and it's got that minus sign there. It's that bugger, okay? But remember it. So the positive frequency part of the field goes as e to the minus I omega t. Okay, there's some stuff at the front. Okay, there is an operator there, which we'll come back to in a moment. There's a mode function there, which if it's in free space with a plane wave, is just some quantization volume at e to the ik dot r. And a polarization unit vector, there's the frequency term. But the critical thing is that here's our operator, that's an annihilation operator, and they don't commute. So the Heisenberg uncertainty relations between the creation and annihilation operators are like so. So if I take the vacuum state, the ground state, and add with the creation operator at frequency omega, I end up with a 1 quantum state. Okay, and then quantum state, you just apply it repeatedly n times, and you worry about normalization. Okay, so that's the standard simple harmonic oscillator. How does that reconcile with the idea of this fuzzy ball of excitation that you could think about as a travelling excitation that whizzes from place to place? So what Vladimir Buzek and I tried to do is to actually demonstrate how you could reconcile that, because excitation of a normal mode is a static property. You've got excitation, nothing happens, it doesn't move. So how do you reconcile it with light moving like a lump of excitation that goes from place to place? So what we've done is to build a wave packet. Wave packets can then move. Okay, so we take a really big box. Okay, you find the modes in the box. You take a lot of them. Okay, you distribute one quanta of excitation, h bar omega of excitation. You superpose them amongst those normal modes. And what we'll do is we'll put a frequency distribution in. And in fact, what we'll do is we'll build a Gaussian wave packet, just for the model. So we'll build a lump of stuff, which is a Gaussian. So in a 2D model, x and y, x, y, we'll make a Gaussian superposition of all of these modes. Okay, so this little model, what we've got is 256 modes in the x direction and the y direction. Okay, and we'll put h bar omega's worth of excitation into it. Okay, and then what we'll do is we'll just numerically solve the Schrödinger equation for that 256 by 256 state vector space. Just exactly solve it numerically. And what you can see is a little blob that just freely propagates. And you can see that it's spreading out in the y direction because of the localization of the k vectors within the Gaussian wave packet. So if you wanted to think about a lump of stuff or excitation that moves for a photon wave packet, that's how you do it from first principles in terms of Schrödinger's equation. Okay. Right. So that's just a photon wave packet, and that would reconcile the idea that a photon is an excitation of one of the normal modes of the system with the idea that a photon is this fuzzy stuff that propagates. Okay? The fuzzy stuff that propagates is a superposition of all the stationary modes of the system. Right. Okay, so let's start thinking about interference. Interference started very much with Thomas Young. Thomas Young published a paper in the Royal Society, his Philosophical Transactions, about interference. He got absolutely character assassinated in the response by people who said, no, Newton said this wasn't so, therefore you are totally misled. And he gave up and went to work on the decoding of Egyptian scripts instead. Okay. Fresnel, about 15 years later, showed us, no, there's Thomas Young, and if you want to know more about Thomas Young, because he was the most extraordinary man, Andrew Robinson's biography of Young is a terrific read about how the wave theory of light evolved. Now, so the idea of a wave nature of light persisted, Maxwell's equations, then put it on a firm foundation, but there was a student of J.J. Thomson's in Cambridge. J.J. Thomson had heard about Planck's idea of light quanta, and of the black body radiation, and then about Einstein's ideas about light quanta. So J.J. Thomson said to G.I. Taylor, who was then a student, he said, what happens if you take an interference experiment at extremely low light levels, so there's only one quanta on average in the apparatus at a time. Does interference persist? Okay, so he suggested this as a problem to G.I. Taylor as a student. Okay, there's a picture of G.I. Taylor. He became Sir Geoffrey Taylor, the doyen of fluid mechanics. Okay, the Rayleigh-Taylor instability is Taylor's. So that's him in old age working on a fluid experiment. But when he was a student, he decided to take this idea of J.J. Thomson seriously, and he set up an experiment in the nursery of his house at home. Okay? And he used these extremely long exposure times. One of them was 2,000 hours. 2,000 hours is basically the length of a long vacation in Cambridge. So he set it going and went off sailing boats, came back and developed a photographic plate. And at one point he said the lowest light intensity he was using was equivalent to that of a standard candle, whatever that is, burning at a distance of rather more than a mile. Okay? And he saw no, as long as you had a long enough exposure time, he saw no diminution in the fringes. So the first person that looked very seriously about whether interference persisted down at the single quantum level was Geoffrey Taylor. Okay. But of course, that's on average one quanta in the box. What about if there's precisely one quanta? That took a bit later. Okay, but it's worth bearing that one in mind. So the first published paper of G.I. Taylor's was actually looking at quantum optics. Right. So, if we could build a wave packet from first principles, let's do interference from first principles. So what Vladimir Buzek and I have done here, you can't really see it unless you're standing about there. Can you see that there's a blue line there? Most of you can't see it. You can, can't you? So he's my guarantee of truth. There's a blue line there, with a little gap just there. And the blue line is a raft of two-level atoms. Okay? A whole line of two-level atoms. And what we've done is the same Gaussian superposition of photon states to start with. So the little blob that starts is my Gaussian superposition, which I'm throwing at a line of two-level atoms with a gap just there. Okay? So this time I've cranked up the number of modes a lot. It's 512 modes by 512. Okay? We've got a line of two-level atoms there. Okay, they're all on resonance with the center frequency of the wave packet. And then what we've done is a multi-mode version of what's called the James-Cummings model, which will pop up later on. And then just exactly solved it, okay, numerically. that's a complete ab initio calculation of single slit diffraction. Because these are active atoms, you see that they reflect the light, and then some of it's transmitted, and you see it's diffracted. Okay? Right, so there's a first principle calculation of single slit interference using active atoms as the mirror. Okay, that's the slits. But if you can do it that way around, okay, you can certainly do two slits, can't you? Okay. So you can't see the line of two atoms, but they're there. We've got two holes in them. Again, loads and loads of atoms on resonance. Exactly solve the Schrödinger equation for this lot. 512 modes by 512 modes. Okay, exact solution. And there you see two-slit interference. Well, at that point you say, that looks exactly like Thomas Young's two-slit interference. That's because it is. There is no quantum theory of diffraction. There's no necessary quantum theory of diffraction if all you're interested in is mean values of the photon excitation number. Okay? Because the Helmholtz equation that determines the spatial evolution of these things is the same in quantum theory and classical theory. Okay, so there's no quantum theory. But on the other hand, occupation numbers are the domain of quantum physics. So if we start to look at fluctuations in here, you see something different. Okay? So the geometrical distribution is exactly the same. There is no quantum theory of that. But on the other hand, if you start looking at whether that's occupied or the next one is occupied, or the joint probabilities, you'll see something else. Okay. Right. So the first person to start looking at correlations, well, this isn't three people. A lot of people think it's three people, Hanbury, Brown and Twiss. Hanbury Brown is one person, and I've hyphenated it, even though Hanbury Brown wasn't hyphenated, just to remind you that there's actually only two people there. I cannot find a picture of Twiss, although I've met him. If you do a search, Alan Aspey, my friend in Paris, thinks he's found a picture, but I'm not absolutely convinced it's actually of him. Okay, but this is Hanbury Brown, and what they were doing in Manchester in Lovell's group at Jodrell Bank was trying to do something different to the Michelson interferometer. Michelson interferometer, remember, was wavefront splitting at great distance and bringing the wavefronts together. Amplitude interference. It's incredibly difficult. You can do it at radio frequencies, but optically it was hard work. Okay, so what you do instead is compare the intensity over there with the intensity over here. And that's an intensity correlation. And to demonstrate the effect, what he did is to look at this thing optically first. Okay, so what he was basically doing, it translates it into optical terms, is we look at the intensity at time t, and the intensity at time t plus tau. And then you normalize it. And so if you imagine a beam splitter, that's the first time the beam splitter's popped up, in comes the light, some gets transmitted, some gets reflected. You look at the reflected intensity at time t, and the transmitted at time t plus tau, and you can vary tau by moving that distance, and then doing a coincidence experiment. So that's the Hanbury-Brown experiment. They did it with a spectral lamp. They saw the effect that they needed, and they saw this idea of photon bunching. And when that was published, a lot of people immediately denounced them as cranks. Okay, a lot of people said this Hanbury-Brown stuff cannot be true, because in Dirac's textbook, which is clearly the Bible, and therefore indisputable, there's a statement that photons only interfere with themselves, not with each other. So what was going on? Completely naive view of photons, but nevertheless they were denounced by a lot of people. So Ed Purcell in Boston started to look at the counting fluctuations and said, oh, this is real. But at the same time, cosmic ray people who started to worry a lot about counting statistics in cosmic rays said, we know about counting, we could go and look at this. So my friend Leonard Mandel, who started his career at Imperial College, actually did all of the early work on photon correlations at Imperial, started to worry about this too. I believe the Hanbury-Brown Twiss experiment is actually the beginning of quantum optics proper. You know, it is the pioneering experiment. Why they didn't get a Nobel Prize, I do not know. Okay. So what happens if we go down to the single photon level? Actually, I ought to have gone back a bit because I skipped something. This correlation function G2, this is a language developed by Roy Glauber, and for classical fields that obey a Cauchy-Schwarz inequality, what you know is that G2 with a zero delay, time equals 0, has to be greater than or equal to 1. And of course what we're interested in, as we'll see in a moment, is the G2s being less than 1, which is completely impossible if you think of the stochastic fluctuating electromagnetic field as something with a positive valued probability distribution. Never mind. Avery Brown was looking at bunching of thermal light and we're seeing these G2s which were excess fluctuations. Right, so if we go down to a single photon level and we fire photons one at a time at a beam splitter and look either at there or over there, the idea is that either you get transmitted or you get reflected. What's the correlation between these two? And they were the questions that people started to ask at the beginnings of the 1970s, end of 60s, early 70s, when people started to think about developing single photon sources. Okay, right, so beam splitters. You can do an ab initio calculation of mirrors and slits. You can do an ab initio calculation of a beam splitter. One tends to think of beam splitters as entirely passive devices in quantum optics. But what I could do is to take a line of two level atoms, there they are, a bit more visible this time. Okay, right. So I've now got 881. Don't ask me why it was 881. Two level atoms, but this time I've detuned the resonance frequency of the atoms a little bit below the center frequency of the Gaussian wave packet that I put in. Because it's now detuned, it's dispersive rather than absorptive. Okay? And that acts as a beam splitter. So there's my wave pack, look. There's my wave pack coming in. Transmission. If you look very closely, you see some nice fringes when it hits that. So that's an ab initio calculation of a beam splitter. But it's quite fun because what you can do is you can look at the density matrix of the fields as they emerge over here, with a trace of rho squared, for example, of the density matrix of the field, and you can see that it's pretty pure. In other words, the idea that this is a passive beam splitter rather than active that gets entangled with the light is actually not bad. Right, so that's ab initio calculation of mirrors. Now, once you've done this, you can start playing games about these things, and Vladimir and I did. So, there's mirrors. You saw lovely interference pattern there, you see it? You can do billiards. I'm not doing any naked billiards in this talks. You've been reading the newspapers recently. Isn't that neat? I love that one. So these are all rows of two-level atoms, some detuned to form beam splitters, some on resonance to form mirrors. So you can build all these things. You can build internal cavities, see how these things propagate. You can actually start worrying about barrier penetration when you do this sort of stuff, and that's quite neat. That's nice, because that's the standard Michelson interferometer. As it comes out a different way to where it went in, and you can start worrying about phase relationships between incoming and outgoing light. Okay? That's lovely, because then you've got a mirror that's curved. And of course, I'm old enough to remember lasers when they first started. Okay, 1965, the first laser I ever saw was down in the basement, would only operate very late at night on amazingly rigid bars and so on. And after a while, physicists started to think, instead of having flat mirrors, you could curve them a bit, and then the alignment problems go away. It did take 3 years to work that one out. Okay? So instead of having that, do that. So the idea of a confocal resonator took a while. It took Tingy Lee, basically, and Foxley modes. So you like that one? That was neat. This one is neat because this is what I did for Tony Siegman. Well, that's an unstable resonator mirror. You can see how, with an unstable resonator, with that sort of curvature, there's this tremendous blob as it firing out. It's actually amazingly good. And for high power lasers, that's what you should use. Okay. And then you start thinking, oh, what the hell, I'll do pinball now. So that's the first principles, ab initio, QED, supercomputer calculation of pinball. That's the biggest calculation on a supercomputer I've ever done. Totally pointless, but very fun. Okay, so you get the idea. You make a Gaussian wave packet, you propagate it. Two-level atoms can form mirrors if they're on resonance. They can form beam splitters. If you have them off resonance, then it's dispersing. And you can do it all from first principles. Right. So just to demonstrate what you can do with this, imagine you have a 1D cavity. Those were 2D ones because they get 3D pictures. In a 1D cavity, what we did, and this involves Vladimir, Musha, Kim, a whole raft of people, is we'll take an atom in a cavity, and it's 1D, and we'll decompose the modes, and we'll solve the Schrödinger equation exactly again, and we'll start this time with the atom excited, not the field, but the atom excited. Okay? And we'll look at the property of excitation of the atom, and what I'll do is I'll put that atom in specific places in the cavity. I can put it slap bang in the center of the cavity, that's with a delta R of 0, or I can move it by little bits, lambda by 8 for example. I've got a lot of modes because it's a big cavity, and I'll do the same decomposition, I'll let it rip, and so what you see is exponential decay. Okay? Because the atomic excitation is shared out in those hundreds of modes, and out it goes. Okay? But because it's a finite number of modes, there's a Poincare recurrence. Okay, so there's the recurrence, and the recurrence depends on whether you're slap bang in the center or not. Okay? Because you need to get the constructive interference working right to re-excite the atom properly. Okay, so there's exponential decay, and there's the recurrence. And that recurrence time will go off to infinity as the number of modes becomes infinite. Okay? And if you look very carefully right at the top, what you'll discover it's not really exponential at that point. There's actually a quadratic time dependence issue. But that quadratic time dependent region gets smaller and smaller as the number of modes increases. Okay? And I'll come back to exponential decay and its variance later on. Okay. I mentioned Leonard Mandel, actually the first person to try to do quantum correlation experiments at the single photon level was John Clauser, who published a paper in 1972 using the cascade, the two-photon cascade experiment that he did the Bell inequality experiments with. People forget that John did that, but it was published in 1972. If you put it into modern language, he actually observed anti-bunching. Okay? So the Clauser experiment, if you look at it, because it's phrased in different language, you didn't realise that that's what he'd done. In fact, John didn't realise that's what he'd done until the Kimball experiments some years later. But the main engine for single photon interference was very much developed by Leonard Mandel, that's Len, at the office next door to me in Rochester, when I worked in Rochester. Extraordinary man, equally talented as a theoretician and an experimentalist. Jeff Kimball was one of his students. So when Kimball and Mandel saw the first anti-bunching experiments, the first we knew about it was going to lunch with Len, picking up Fizzer letters in the mailbox as we went to lunch, and there was the paper. They hadn't said a word about it, even though we had lunch with each other every day. Okay, anyway, there's Len. And what he was doing was a source of single photon pairs, and of course it was a parametric down converter. Okay, so parametric down converter, weak efficiency, shuts up photons in pairs. So there's the state vector, and what mainly comes out of a param low gain is mainly nothing at all. Okay, it's mainly the vacuum. And there's a little bit of a two photon state, 1, 1. 1 in this mode, 1 in that one. Signal and idler, basically. There's a little bit where 2, 2, a little bit 3, 3, and so on. So what you can do is to make this a source of heralded photons. So what you can do is to say, right, I'll use that detector to be triggered by the detection of a photon over here. Because they're born in pairs, see 1, 1, 2, 2, 3, 3. If they're born in pairs, when that one's detected, you know that one's coming. Okay? So you have an avalanche photodetector over here, triggers that APD over here to say, right, that one's coming. So So you do experiments with the heralded photons saying, with this trigger, something's coming. And so what Len started to do is a whole raft of experiments on the internet, starting with Leonard Mandel. John Rarity and his group in Melbourne, pretty close behind them on that one, literally within a year. And that then became the engine for a whole raft of these things. Okay. So let's have a look at, going back to beam splitting now, down at the single photon level. I mentioned John Claus's experiments in 1972. Okay? And then there's Kimball and Mandel. Kimball and Mandel did a beautiful experiment in resonance fluorescence showing anti-bunching, showing this G2 parameter, which in terms of annihilation and creation operators for a single mode, you can write like that. So it's A dagger squared, A squared, and then normalized. And what they showed is that G2 dipped below 1 for single photon sources. In other words, they were anti-bunched. The experiment I like to show is the Grangier experiment. This was Philippe Grangier's PhD thesis in Paris, working with Alan Aspect. What he did is he had a source, which is very much the source they developed for the Bell experiments. Now there's a little story about this. When John Clausen started to do the Bell correlation experiments at Berkeley, he wasn't given tenure, because after all he was only investigating things that everybody knew was true. Quantum mechanics was right. And he didn't get tenure. And John then spent the rest of his working life at Livermore with quantum stuff as a hobby. And what he was really doing was high power laser stuff. So John didn't get tenure. Okay. When Philippe Granger and Aspect started to worry about these things, John Bell went to Paris to talk to them, and John Bell's first question to Alan Aspect was, "Do you have tenure?" Alan said, "Yes, of course." He said, right, keep going then. Because he was really worried about what happened to Clauser who didn't get tenure. And now what they did is they built initially a version of the Clauser experiments again. So they had a source of 2 photons. Okay, it was a cascade source. Calcium, 1 photon, another photon, different colours. Okay, you have a detector. This one then acts as the trigger to turn something over here where you can do a correlation. So you have a beam splitter, 2 photon multipliers. So you're doing a Hanbury-Brown twist experiment that's triggered by the reception of this one. So you know you're definitely looking 1 photon at a time. Okay? So first thing to check is the photons are indivisible, and that's what was done. And there's a very beautiful graph which shows you the coincidence count. So there's the classical domain. I told you that the G2 has to be bigger than 1 if you have a classical stochastic field with a positive probability distribution. So there's the classical domain. There's the experimental results. And it just shows you that it fits very beautifully, it's quantum theory, down at the single photon level. So that's the Grangier experiments dipping right down to 0, which is what the Kimball and Mandel experiments could not do because they had a Poisson distribution of atomic sources into their atomic beam. Okay? Here they could guarantee they were done at a single photon level. Okay, and later on it's done with ions, rather beautifully by a number of groups. Okay. Right, now let's go back to field uncertainties and fluctuations. Okay. So instead of decomposing the field in terms of annihilation and creation operators, B and B dagger, what I'll do now is to write the field down in terms of, I think it goes as cosine omega t, and I think it goes as sine omega t, in other words, the quadratures. And if I plot the field variation as a function of time for the quadratures, what I could find, well, you get the sinusoidal variation with time, because it's a single mode field, it wobbles up and down at frequency over 0. But if I look at the quadrature that goes as B plus B dagger, and look at the quadrature that goes as B minus B dagger, that's like a coordinate, that's like a momentum. Okay? And in that example, what I've chosen is an example with a Q noise, the thickness of the line is reduced, but the P noise is increased. So that's squeezed light. And in terms of a phase-space diagram of P versus Q, what I've got is a rugby ball shape which is compressed in that direction, so delta Q is small compared with delta P. It's a bit like toothpaste. When you squeeze toothpaste, squeeze it in here, it comes out there, because the area has to be such that it satisfies the commutation relations. Okay, and the Heisenberg uncertainty relation demands that area be at least in the right normalized units. Okay, so that's squeeze light, major resource in confirmation processing, and that's single mode squeeze light, and you measure it by homodome detection. Okay, so let's start thinking about non-classicality. And my little story about tenure comes back again. Okay, one of the nicest ways of demonstrating non-classicality is to compute the Wigner function. So that's usually in Wigner. Okay, and so if I take the vacuum state and I plot the Wigner function, I get this nice Gaussian distribution. So there's the Wigner function. It's a simultaneous joint distribution function for Q and P. You take the density operator, and you just basically put a little bit of off-diagonal shifting in it, and then Fourier integrate it. Okay? If I look at the vacuum state, it's positive everywhere. A coherent state, like the things coming out of the semiconductor laser, pretty much, is also positive everywhere. Okay? But if I took a quantum state, and here this is a Fock state, you see these are the Ger polynomials that characterize a Fock state. Okay? And so you can see here a little bit of negativity in there. So if you have a negativity, you know that you can't have a joint distribution function of P and Q that is positive everywhere except a Gaussian. Okay, I'll come back to that in a moment. That's called the Hudson-Piquet theorem. All right. Oh no, I forgot to tell you the story. Okay, so Wigner had gone to the United States by this time, published this paper. It's a deeply cryptic paper because he said this was suggested to him as something that he jointly did with Szilard, and there's no known paper with Szilard. Okay? So donkeys years ago, people talked to Wigner about it, and he said, I can't remember what it was either. Anyway, he wrote this paper, and Princeton didn't give him tenure. Okay? So he went off to Wisconsin for a little while, came back, and finally did get tenure. So somehow quantum optics wasn't terribly fashionable once upon a time in terms of getting tenure. Anyway. Another way of looking at non-classicality, that's not the only distribution function you can look at. You can start thinking not in terms of Fock states, which is the Wigner functions or territory, but in terms of coherent states. This is Roy Glauber. Actually, that's Roy on the day of the Nobel Prize. And what Roy did is to say, we take a density matrix, and now what I'll do is I'll represent it in terms of a coherent state basis with some distribution function P of alpha. And what Roy would say is that a positive, well-defined P function tells you that basically it's nice and classical because you've got a distribution function that's positive everywhere. So for thermal light, for example, it's a Gaussian. For coherent states, it's the delta function because there's only one coherent state. And for non-classicality, if that P of alpha goes negative, then you know, or singular, in fact, you know that you've got something which is not a well-behaved distribution function. I actually prefer the Wigner function, but this is a highly singular thing to work with for some things. And we'll get some examples later on of non-classicality for Fock states and so on. And it used to be said in quantum optics that basically anything with a positive P function was classical. I dispute that. I think all fields are non-classical. You just have to look harder. Okay, and I'll explain what that means later, because what we haven't talked about is discreteness of the excitation number. And I'll come back to that in a bit. So I think everything is non-classical. You just have to put a lot more effort in. So positivity of the P function is insufficient in my view, and I'll show you why when we come to talk about the James Cummings model. Right, so distribution functions for the Wigner function. I explained the phase space. You've got P and Q. If I had a coherent state, I just get this circular block. Equal uncertainties in P and Q. Okay, in fact they'll be Gaussians. Squeeze state, I squash it in one direction, expands in the other, still Gaussians. Okay? So if I take in the wave function, instead of an estimated representative, the wave function representation, I displace in the q direction by a little bit, and then the opposite direction, and then Fourier transform. And if I integrate over all p's, I get the marginal distribution for q. If I integrate over all q's, I get the marginal distribution for p's. Okay? And they're observable. And the Wigner function is the only quasi-probability function which is bilinear in the wave functions and generates the correct marginals. Okay? But negativity is very much difficult. And Vladimir and I have written a long, long review article on these kinds of things in Progress in Optics. Right, so vacuum state, that's easy. That's just the Gaussian blob centered on the origin. Okay, so there's a Q, you just get Gaussian. Okay, there it is. And so the Gaussian state is the only pure state Wigner function which is positive everywhere. That's the Hudson-Piquet theorem. Robin Hudson proved it. Robin was at Nottingham for a long, long time. Probably still is. Anybody? There's somebody from Nottingham here.
He's in Loughborough.
He's no longer there.
No, he's in Loughborough.
In Loughborough?
Yeah.
Oh, okay. He was in Nottingham for years and years. Okay, Robin did most of the work on this, and the Hudson-Piquet theorem shows you that it's the only Wigner function which is positive everywhere. Okay? Now what we can do is squeeze it, squash it up, displace it, add it, and subtract it. So we'll see what happens. So we're going to start manipulating. So there's the Wigner distribution for a one photon state. Okay, so we've got a polynomial again, so you've got Q times the Gaussian, so it does that. Okay, and there's a negativity in the center. Okay, so there's the Wigner function plotted. You can't quite see the spike underneath, which is negative, but there is experimentally measured. Lebowski and Luneck did it. This was almost the last experiment done before the Luneck group came to bits in Constance. Lebowski is now in Calgary. And then you can also do exactly the same reconstruction for a one quantum excitation for ions, and Dave Winan's group did that first. Right, so we did some one photon stuff with beam splitters. Now let's look at two photons. And so if I have a source of two quanta, and I do an interference experiment, there's something quite interesting. If I took a beam splitter and I put a single excitation in the two arms that are coming in to the beam splitter, that one, and look at what comes out, because there's a phase shift on reflection. Okay, you can add up the amplitudes for this kind of stuff. One photon there, one photon there. Okay, because of the phase shift, you get the zero coincidence probability. Okay, because photons are indistinguishable, you get this dip, and that's sometimes called the Hong-Mandel dip. Sometimes it's referred to as the Hong-Mandel dip. I think that's incorrect, because Wu was a co-author. You should remember Jeffrey Wu. So it's Hong-Mandel who did this first. Okay? If you want a nice textbook example explanation of this, it's actually in Feynman's lectures, volume 3. Okay? If you go through Feynman's lectures, he talks about exactly this for bosonic interference. Okay? And that's the vehicle for two-photon interference that you use everywhere in quantification processing. Right, so at this point you start thinking about where's the resource that you could use, and that's something that Vladimir and Yashik and I worried about a long time ago. If you have two classical input fields, you know that you can't get an entangled output. Okay, if I bring a classical field into a beam splitter, what comes out the other side is a product state, which is totally disentangled. You've got to be really careful in some areas to make sure that you've properly represented the coherent state as a coherent state. If you say, oh, it's a weak coherent state, so it's only 0 and 1, I put 0 and 1 through a beam splitter, you've got an entangled output. Okay? So sometimes numerical artifacts can generate you garbage at the end. I might even think of an example of that towards the end. Okay, so if I have a vacuum state, that's a Gaussian, and a squeezed thermal state, that's Gaussians as well, and I jump through a beam splitter, I can get an entangled output if and only if this squeeze state becomes non-classical itself. Okay? If I have a thermal state and a squeeze state, again, it will become entangled, or you get an output field that's non-classical you have to have some non-classical resource to start with. Okay. So in other words, if I had a 2-photon state with 1 and a 1, I get this entangled state coming out. And that's quite a nice generator of non-classicality, where you bring into the beam sort of 1 and 1, and you either get them both in one arm or both in the other arm, but not 1 and 1 again. So you get an entangled state. Right. So at that point, you can start playing with that quantum arithmetic. I'm going to start adding a photon, subtracting a photon. And that's something a number of people thought about. Adding a photon, I guess Girish Agarwal was the first person to start playing with this thing back in 1991, but it didn't really get much attention at the time. Subtracting a photon, a number of people around 2004-05 started to play with it, including me and Ming-Chick, and a lot of experimentalists, especially the groups in Paris, about subtracting photons. And if you add and subtract and start looking at quantum arithmetic, the group of Marco Bellini, I think, has done some extended stuff, which I shall explain. So you can actually start thinking about ways in which you could take a photon out of a field or add a photon to a field. And that way you can start generating non-classical resource. Because one of the things that you cannot do with a Gaussian state is anything that's really terribly interesting. I don't know if Martin might explain a bit more about that at one point. But it's like Martin Plenio has done an enormous amount of work on. Right, so how do you take away a single photon? You do it conditionally again. So I take a beam splitter, I take my state psi, I want to knock out a photon. So what I do is I take a beam splitter, okay, in comes no photons from the other arm, or the vacuum state. So the state here, no photons, and what I'll do is I'll look at the field coming out there, conditioned on getting a clip there. Okay? So I take my state, okay, which is input psi, vacuum state, there's the beam splitter transformation, conditioned on detecting one photon there. Okay, one click. There's the beam splitter transformation. If you've not seen it before, it's a bilinear combination of annihilation and creation operators for the two modes A and B that come in. Okay, so it's A, B dagger, minus A dagger B, and an angled theta. And you, by varying theta, you can make it an equal beam splitter, or you can make it one that basically transmits. And here what we want is a T transmissivity around 1. Okay, so you take that, and if the transmissivity is around 1, you can expand that exponential in the power series. Okay, keep the first term, and then you find that basically when you do that expansion, it's roughly the same thing as the annihilation operator acting on your initial state. So conditioned on one photon being detected over here, the output field is just a one photon subtracted state, the annihilation operator acting on the same. Okay, now if we look at how to add a photon, well, you've got to have one to add, basically. So what you do is you take your state, something, or worry about what something is, and look at the output over here, conditional on the click here. Okay, so there's my initial state. Okay, there's a vacuum state there. That's the only thing that came in. This being look at being splitter. Okay, but it ain't, because what I'm going to do here is squeeze the stuff. So instead of having something in an exponent, because A dagger B is conjugate, what I'm going to do is have A dagger B dagger, a squeezing operator. Okay, so that's a squeezer. So I've got A dagger B dagger, and then AB. I'll assume the squeezing parameter of eta is really small. I've got a power series expansion, and then what happens is when you get really small squeezing, it's just the creation operator. That's what I'm saying. It's like an addition. Okay? So with a param, which is your squeezer after all, you can start adding quanta. Okay, with a regular beam splitter and a detector, you can start subtracting. Okay. So in terms of addition and subtraction, this is Marco Bellini's experiment where he has a dot laser, pumping param, adding and subtracting. It works beautifully well. Okay. Right. So with a 50-50 beam splitter, input, vacuum state, both of them go and click. A conditioned state then is a 2-photon state, It's not much good actually, because you've got both detectors firing. But you can do it. I'll skip that. I'll skip that too. Oh, that's like yeah. I'll skip this because I'm looking at time now. Okay. So that's how the Bellini group actually implemented it. Down converter, pump, psi. This field acts as if there's a correlation operator over here. Conditional and click over there. Okay, good. If you look at subtraction, by the way, it's kind of fun actually. When you look at this zero beam splitter, we do a conditional and click over here. Look at the curve over there. When you've got a squeeze state coming in. Okay, so if I take a squeeze state, the characteristic functions is Gaussian again. I can work out the output field conditioned on one photon being detected just there. There's one photon there in that mode. Okay, and you normalize it properly. And you look at that reduced density operator for the output field, and you look at its properties in phase space. And if you look at the Wigner function at the origin, which is where the negativity would show up, what you find is something different on the transmissivity and the reflectivity of all these parameters. Okay, and then when you look at it graphically, what it looks like, remarkably, is that by taking away a quanta, it starts to look like a Schrödinger cat state. The Schrödinger cat, the first time it's appeared, is alpha minus alpha. This is an antisymmetric coherent solution. Two coherent states, alpha and one magnitude minus alpha. Okay. Just to show that, there's a subtractor state, there's a cat state. And what we did is we looked at the fidelity of cat states versus subtractor states. And depending on the transmissivity, it's not bad actually. It really does look like a cat state. Right, and it works, it works, it works. Violate bells of equality. Right, I'll skip all that stuff. I'm looking at the time. Now, I did make this claim about non-classicality. I actually said that all these fields are non-classical. If you do a bit of work. There's a famous cartoon of Vortex Durex in physics today with a barrier, classical in the quantum world. Okay? There's a quantum world over here and a classical world over here, and somehow there's some sort of a barrier, some sort of boundary. I know this is being recorded, but I've actually said it in front of Vortex as well. That's total crap. There is no boundary between the classical and the quantum world except for money. Okay? You will always find quantum effects if you put more resource in. Okay? The idea that there's a classical emergence in some way, I think is nonsense. Okay, so I think that all of these fields that we talk about are intrinsically non-classical because they're superpositions of number states which are discrete. So if you could find an engine that looks at the discreteness, you would always see this. Now, that's where two of my heroes come in. This is Herbert Walter, who formed the Max Planck Institute of Quantum Optics in Munich. He was a great pioneer of quantum optics experiments in Europe. And this is Serge Roche, the great hero of quantum optics in Paris. And between them, they developed the idea that you could build detectors of radiation that looked right down at the single or few quantum level and saw the discreteness. These things are called micros. The detectors are Rydberg atoms with enormous coupling constants. But when you go to very highly excited states, the dipole moment scales quadratically with the principal quantum number. So instead of having a Bohr radius type dipole moment, you could have something 2,500 times bigger. So enormous quantum antennas that detect this. Okay. So if you can do that, you can start looking at the discreteness of the radiation. And that's what they did. This is Serge's experiment in Paris, where he took an atomic beam. There's a Ramsey loop here, Ramsey loop here. I think I'm probably the only person in the room that's ever operated. When I started my PhD as an experimentalist, I'm probably the only person in the room that's ever operated a Ramsey atomic beam machine. Good, okay, I was just checking with David. It was hopeless and I gave up and became a theorist. So you have a microwave region over here, one over there, you get interference between the two. In that cavity, you're going to make non-classical states. And what Serge was able to do is, by a very clever analysis of displacements and so on, is to measure the Wigner function of the field in the cavity by atomic interference, by putting atomic superpositions through that cavity field. Okay, so enough of that, don't need that. Okay, so here's the James-Cummings model. First time it's popped up, I'm sure we'll see much more of it. Okay, two-level atom interacting with a resonant field mode, a single one. And of course, what happens is you get Rabi oscillations, a collapse, a revival, a collapse, a revival. Okay? You get a collapse because you have for a coherent state in the cavity, you have a Poisson superposition of photon numbers. Okay? But you get a revival because it's discrete. Okay? There's a partial revival if the eigenfunctions in this thing are depending on the square roots of the quantum numbers. So you get and Joe Everly and his colleagues look at this, and experimentally that's exactly what Serge was seeing. You see collapses and revivals. The collapse is because the distribution of photon numbers, the revival is because they're discrete. And the fact that you can see them, even for that maximally classical state, the coherent state, demonstrates that all fields, in principle, are detectably quantum mechanical. It's quite a nice way of actually showing where it all comes from. If you take a field interacting with an atom, and it's a coherent state, what you can do we all know about a Glauber operator to generate a coherent state from the vacuum? Okay, I'll come back to that. You can take the vacuum state and just move it around in phase space, and that's called a Glauber displacement operator. Okay? It's just a linear displacement being, take that Gaussian Wigner function and just move it around in phase space. Okay. Now that means that for a coherent field, I can apply an inverse Glauber transformation for a coherent field, take it back to the vacuum state, plus a classical field, without approximation. So a coherent state without approximation is a classical field of simple amplitude plus the vacuum. If the vacuum plays no role in your experiment, i.e. spontaneous emission, it's a classical field. Okay? So so what I'll do is I'll take, as I've said, the coherent state is a vacuum field plus classical field of super amplitude. So I'll take a two-level atom interacting with a classical field. It just oscillates up and down, Rabi oscillations. But every time you're up in the upper level, the vacuum field can interact with that excited atom to give you spontaneous emission. It's only into a single mode, but it goes from there with no photons in the cavity to there, ground state with one photon in the cavity. Okay? That's just the A dagger acting on that upper level. Once you're into that one photon state, you go up and down classically with a Rabi frequency. Once you're in the upper state, the A dagger can generate another spontaneously emitted photon. This time you've got two photons in the cavity. I can go up and down classically. Okay? Once I'm in the upper level, the vacuum field can couple again. I get three photons. So what you get is a cascade of quantum generated eigenfunctions, starting with root 1, root 2, root 3, root 4, slowly building up. Okay? And they begin to beat against each other, that's the collapse, but they're discrete, that's the revival. And that's like the whole Radmore and I developed about 1 million years ago. Okay, so Einstein's absolutely right. Quantum randomness, the spontaneous emission, is absolutely key to everything. Right, you're going to tell me there's some coffee ready, so the conclusion. So thank yous first. I've got an awful lot of people. I've been very lucky with my graduate students. So Steve Barnett was my first graduate student back in the UK. I mentioned Peter Maloney earlier. Vlada Boucher, after Echo, was my student in Oxford, and we shipped him. Martin was postdoc with me, and then took my group over, and led it with great distinction, Martin. You're welcome to come back. Paul Radmore, I just mentioned, Barry Sanders was my student at Black Cove, we will see on Wednesday? Thursday? Oh, yeah, okay. And I work with lots of folks that have been fun, do cheap jokes next. No cheap jokes next. Cheap jokes next time. Okay, so what I've tried to demonstrate, because I thought it'd be useful to set the scene right at the beginning, is what constitutes non-classicality. How would you know that things are non-classical? What would you do to determine it? How can you manipulate these states? I'm around right until Thursday morning, so I'm happy to talk with folks and so on during that time. I think you want to take this for coffee. Thank you for listening.